Hello everyone, this is lecture A4 of PEC. After the preparation from lecture A1 to A3, we finally face the most important concept of this part, that is the convolution integral. We will introduce why we need the convolution integral and what function we can realize with the convolution integral. Firstly, we need to review the importance of the zero-state response, on which we've discussed in lecture 51. Let's look at this exercise. This is a voltage source, a resistor, and a capacitor series circuit. The initial value of the capacitor's voltage is 0, that is the zero state. Our interested variable is UC. By applying the three elements method, we can easily get that when the excitation is US, the response is this. When the excitation becomes twice of the former value, we can easily know the response also becomes twice of the former with the three elements method. Similarly, if the excitation is the sum of the two excitations, we can also easily know the response is the sum of the two former responses with the three elements method. What do they mean? The second expression means homogeneity. The third expression means additivity. In other words, it's a linear relationship between the excitation and the response of zero-state circuit. This point is very important in this lecture. The following discussion is on zero-state circuit. For the non-zero state circuit, that is UC or IL, has initial value, we will divide the response. Firstly, solve the zero input response, and then solve the zero state response, and finally find the full response. We will discuss it in lecture 51. Next, we suppose this circuit is the zero state, but the excitation now is no longer a DC voltage source, but can be any excitation. For example, it's such a random waveform. As I've discussed in lecture A1, it can be any excitation like the sound of mine. But how to solve the zero-state response, that is UC, under this excitation? Firstly, we need to divide the time. In other words, we divide the time axis of the excitation from t equals 0 into several discrete segments. The length of each segment is delta tau. Of course, delta tau is changed with our calculation ability. The stronger our calculation ability is, the smaller delta tau could be. We think in the every time segment, for example, from 0 to delta tau, the excitation's value is constant. From delta tau to double delta tau, the excitation is another constant value. So the whole excitation can be seen as the sum of several pulse functions and their delays. How to comprehend it? You see, the sum of several flat waves can approximate to the former excitation as long as delta tau is enough small. How to deal with these flat waves? We can only pick out the first flat wave and treat it as a pulse wave like this. We've discussed this pulse wave in lecture A1. The second flat wave can be seen as a delayed pulse wave, which is a delayed delta tau. The height of the two pulse waves are different. The kth pulse wave is delayed k times delta tau, and its height is different from the previous waves. By dividing the time axis, we can treat the whole excitation as a sum of several flat waves, and these flat waves can be seen as several delayed pulse waves. Because the input-output relationship of the zero-state circuit is linear, so if the excitation is a sum of several delayed pulse waves, the response is the sum of the responses with these delayed pulse waves. We've discussed the whole process in lecture A3. In this lecture, the limit of this process when delta tau tends to 0 is the convolution integral. With the convolution integral, we can solve the response of any excitation. This is the idea of our following derivations.